Alright, so this is lab 4 oscillations. The purpose of this lab was to compare the predicted motion and experimental motion of a mass oscillating at the end of a spring. So in this experiment, the system was the spring, the earth, the mass, so basically everything, and the surroundings were nothing. And the methodology was that we used a video of oscillating mass and tracker to track the X and Y motion of the mass on the spring, and we generated a computer model of this data using GlowScript. The experimental data and computer model were compared, and the energy changes were also observed. The results were that the Y direction was very similar, the X direction had differences, but energy was overall conserved. So the fundamental physics principles that this lab used was Newton's second law, which stated that momentum is proportional to force and conservation of energy, meaning that energy is neither created nor destroyed. And as you can see on the right-hand side, these are the equations that were used. The first one was just force equals mass times acceleration, and that translates to F net equals the sum of the forces. Then we also have that the change in energy is equal to work, and that is equal to the change in kinetic energy plus the change in potential energy, and that is equal to 0 for this experiment. We have the two equations for energy. So kinetic energy is 1/2 mv squared, and potential energy is mg delta h. We also have spring potential, and then we have the velocity update formula, the position update formula, as can be seen by number 5. We have the formula for the period of a spring, then we have the formula for a spring constant, and finally we have the formula for spring force, as well as the formula for the relaxed length of a spring, as can be seen by number 8. And all of these will be used later in the slides in the experiment. So here's the coding. So right here we have the initial conditions which were taken from the video. In the middle section we have gravitational constant, spring constant, and a relaxed length of spring, which was also taken from the video. Then we have calculations to find L, L hat, and S right here. Then we also have the calculations to find the energy values, including just the total energy. And finally here we define that as the initial energy. Then we calculate the gravitational force, then the spring force using the spring force equation, then we add those two to get F net. Finally, we use the momentum principle, aka the velocity update and position update formula, to update the ball's position and velocity, or I mean the mass's position and velocity. Then we update the information on the spring. So we calculate L, L hat, and S again based on the changing position and slash velocity of the spring. And then we calculate the energy changes again for the final energy. So we're calculating kinetic energy, change in kinetic energy, gravitational potential energy, then the change in that, spring energy, the change in that, and then finally the total energy. And then we calculate change in energy, which is just energy final minus energy initial, and that value should be 0, which is what we're going to see in the next graph. So this is the change in energy versus time graph right here. As you can see, the change in energy is at 0, meaning that if you subtract the top line and the bottom line, then you would get 0, meaning that the change in energy was 0. This is the position versus time for y. There's a little bit of offset here, which may be due to coding or just experimental error, which we'll talk about later. And then this is the x position versus time, and there's a lot of offset here, and that could just be due to a coding error. Some errors are that the center of mass may have been incorrect, work is actually being done on the system, and the graph for the x position, which stated before, has a different starting point slash amplitude. According to the graph, the energy principle is satisfied because there are no forces acting on the isolated system. This means that the change in energy is zero, which is what the graph shows. Only the types of energies change, not the overall energy. Then finally, we have the calculations for the period for both the x and the y, and they're actually pretty close, just a couple of seconds off.